All right, hi guys. Do I do my own slides? All right, so this is work I'll be presenting, laboratory work, trying to understand the extent to which we can simulate the ability to detect not just water ice on the surface of the moon, but discriminate between water frost and excavated subsurface ice using remote sensing and infrared wavelength with specific application potentially to Trailblazer, because with Viper-Gone, our next best chance is use Trailblazer to determine if there's subsurface ice. The only way you can do that is by looking at the surface and being able to disentangle the signatures of the ice. Keep in mind that this material is going to be most likely intimately mixed in with the regolith. Okay, so I don't need to talk about PSRs to this group, but I should remind us of what the different forms of water ice can be. We really don't know anything about the water ice on the moon. We only have one ground truth, right? But it's most likely that primordial water ice is going to be blocky, right? To some extent, it will become heated due to millions of years of impact bombardment. And certainly once the water ice is excavated up to the surface, here we go. It will be finer grained. And what's not shown here is that there may be an active process for depositing frost on top of that. So we need to disentangle all these processes in order to stand a chance at detecting the signatures of what was originally bulk water ice and not just frost. The way we do this is to look at the various grain size effects at the infrared wavelengths. Here's an example. Developed from albedo models, and you can see strong infrared bands at 1.5, 2 microns for no reflection peak at 3.1, and volume scattering in the smallest of the finest grain ice at the 4 and 5 micron region. All these are potential signatures, including the ratios. One way we don't want to do it, which is, well, all models are wrong to some extent. Some models are useful. This model is not. This is a purely aerial mixing of an orthosite spectrum with one particular grain size of multiple grain size of water ice at a certain percentage, whatnot. But the point is that to the extent that it may be right, frost will have a very strong ratio between, let's say, two of the neighboring bands, 1.5 and 1.25, or 1.5 and 2 microns. Excavated ice, which is a large grain, will have a much smaller ratio. Would this persist when you look at intimately mixed water ice and regolith? And the answer probably is not as much. I'm basically giving you a preview of what our results are. So way we went about experimenting with this, we did 2 different experiments. An initial one was done in the visible through near infrared out to 2.5 microns, where we created water ice. We simulated micrometeoroid bombardment by using a laser, and we looked at this with infrared spectrometer and then allowed frost to get onto it. Very, very initial measurements. Then later, we actually created pellets of mixed water ice and regolith simulant, and we use sieve fraction of water ice. And we use liquid nitrogen wet sieving to create these sieve fraction of water ice, and then mix it in with the regolith simulant itself, created pellets, and then use that. All right, so these are the people who actually did the work, and of course I came instead of them. They are actually still in the lab making measurements right now, getting ready for abstract to AGU. But the hard part, and they're having fun. I got to admit, they're having a lot of fun in the lab, truly. The hard part is sample preparation. It is hard to keep ice from getting icy, to keep it from getting frosty. That's a major challenge I've had that we're continuing to work on. It's also turned out to be hard to keep the water ice mixtures from desiccating as well, surprisingly enough. But regardless, we have solutions to this. This is the first experiment where simply did pure water ice. Bulk ice would be the, how much time do I have left? 5 minutes? The bulk ice is in the middle there. Laser radiation are the, it's brighter areas where we scoured it with a laser, and then we allowed frost to deposit back on top of it later. And you see the individual specs where bulk ice is very dark at 1500 nanometers in longwards, and generally just dark. Frost has no 1.25 micron band, and shallower 1.5 and 2 micron bands. And the I guess excavated or micrometeoroid bulk ice still looks kind of like large grained ice with a little bit, of a maybe frost characteristic to it, even with frost on top of it. The point is, okay, maybe this could work, this whole idea of looking at grain size effects and all, but this is pure water ice, right? So this is not at all what we need to be doing. The next step is to actually look at the mixtures of water ice and the regolith itself. In order to do that, we had to make the ice at different grain sizes so we know what we're doing. Again, this is our albedo model. I'm about to show you why we think we got these SIP fractions right, even though we couldn't take very good pictures of it, of three different models on the left, three different grain sizes on the right are three different sieve fractions. Generally, they're very similar shape. Don't look too closely at the numbers. You see they don't correlate all that well, but it's not bad. What I find most interesting is that the middle grain one right here has a couple reflection peaks on it, characteristic of very fine grained frost. You know, this is proof that at least we kind of know what we're doing, that, oh yeah, we can see when we're contaminating our sample, right? So we know when we've made mistakes. Also interesting, for now reflection peak, changes in size. I didn't really expect that for a single combination of incident and emission angles. Other than that, it looks pretty good. Okay, so let's go ahead and make our pellets. Here we go. There's a pellet right there with water ice mixed in with it at 10%. There's no way you could tell by your eye it has water ice in it at various grain sizes we tried. So not surprised at all that shadow cam saw no evidence for this in its reflections measurement. Just there's no evidence even in the laboratory that works. But what we did notice that the very first measurements make, the sample's already desiccated. So in the process of making the water ice pellet, we lost the isomer. This is preliminary work. I'm happy to show here, but it's not going to be published yet till we figure all that out. And these are the spectral features we think we see. What's interesting, H2O here, OH, et cetera, probably carbonate, you know, impurity and all. H2O here at 1.9, that's adsorbed water. That's not water ice, even though this is at, what, 165 Kelvin. Desiccated surface. After lasing, though, we blasted chunks out of it, and that exposed a water ice rich area. And you can see the water features here and here. Shallow, similar to one of the first talks we saw in modeling. So very consistent with some of the modeling results we saw earlier today. And at deeper band here, what is missing? The Fresnel reflection peak, which I think is somewhat interesting. This 6 micron band doesn't increase because it's not present in larger grain water ice. You let it sit overnight at 10 to minus 7 torr, you still precipitate some frost out on top of it just through molecular deposition, and the bands increase a little bit. Some there, that band doesn't change. The band ratio doesn't change that much here, and neither did the 3 micron bands. That's somewhat interesting there.
1 minute left.
And then we allow some frost to form on top of it. And immediately you see what pure water ice looks like on top of and this is very thin. You can't even see it by eye almost, all right? Very hard to see. Fresnel reflection peak. So the way to detect frost from maybe excavated ice is the presence or lack of the Fresnel reflection peak and the ratio between these bands and the 3 micron band right there. So in conclusion, laboratory reflection, you can read this for yourself. I was personally a little bit surprised by no 6 micron feature in the water. I still thought about it. Okay, fine. See the 6 micron band, that's adsorbed water. Don't expect to use it to map out water ice. The 1 and 2 micron bands are useful, but they aren't as useful or present, not as useful as I thought. We might be able to use the ratios, but you saw the bands are quite shallow, and that was a 10% mixture. In reality, you'll probably have to use a combination of the 1.5, 2, and a 3 micron band, all of which Trailblazer sees, right? So what we're hoping to get from this is the ability to develop a algorithm that Trailblazer or somebody can apply to the data when they get it back so they can robustly determine if what they're seeing is frost-free, that'd be easy, or excavated primordial water ice. And anything else that I missed? That's about it. Thank you.